Court is in session. The defendant, your upcoming Cambridge IGCSE physics exam. And the stakes? Well, they're your final grade boundaries. Every single year, thousands of students walk into that 6025 physics paper totally confident in their memorization, only to get absolutely crushed by the examiner's mark scheme for hidden practical errors. In this explainer, we're putting your answers on trial, and the evidence is going to be our ultimate witness. If you want to lock in those top marks in forces, you need to think exactly like the person grading your paper. Let's get straight to the evidence.
All right, picture this. You're standing in front of 3 doors. Behind each one is a completely different student's approach to calculating a spring constant. Door number 1, it relies purely on just reciting the textbook formula. Door number 2 involves plugging raw numbers into a calculator and, just scribbling down the very first decimal you see. And door number 3, that one combines the formula with specific experimental evidence, units, and the correct significant figures. So which one actually secures the grade boundary? You guessed it, only door number 3. Let me show you exactly why those first 2 doors are massive traps that will absolutely bleed you critical marks.
So let's really dive into this. Take a look at these common revision failures. These right here, these are the real culprits stealing your marks. See, ordinary formula memorization totally falls apart when you're faced with practical skills questions. Honestly, you can know the equation for moments or the spring constant perfectly, but if you drop the units, or if you round your numbers way too early in a multi-step calculation, or say mix up your dependent and independent variables on a graph axis, the examiner is going to penalize you hard. It's these painful, everyday mistakes, not a lack of actual physics knowledge, that are the real reason students lose those top grades.
Okay, the absolutely crucial point here is getting our foundation rock solid before we even look at the data. Here is your first quick win. When the exam asks you to state Hooke's law, you have to use the precise exam-safe terminology that the Cambridge mark scheme practically begs for. Notice this exact phrasing, directly proportional. It is not just as one goes up, the other goes up. No, it has to be directly proportional. And then there's the critical caveat, provided the limit of proportionality is not exceeded. You've got to memorize this exact wording because anything vaguer than this will literally be struck from the record by the examiner. Now, what's really fascinating is how we actually apply that strict definition to real-world experimental data. Look really closely at this table, comparing load in newtons against extension in millimeters. I'm challenging you to act as the examiner right now. Can you spot the anomaly where the spring constant just completely breaks? Let's walk through it. Look at 1 newton. The extension is 2.5. At 2 newtons, it doubles to 5.0. Perfectly logical, right? So following Hooke's law of direct proportionality, at 3 newtons, it absolutely should be 7.5 millimeters. But wait, the table says 8.5. Bam, there is your anomaly. Now, the limit of proportionality hasn't actually been exceeded yet, because if you look at 4 newtons, we hit 10.0, which lines up perfectly with our 2.5 multiplier. Therefore, that 8.5, that's a pure experimental error. Identifying the stuff on the fly is exactly how you secure those heavy data analysis marks.
So you're probably starting to see how looking at the data critically literally changes the entire game. And listen, in just a moment, I'm going to show you the exact examiner clue that changes your answer completely. But first, you need the framework that makes that clue super obvious. Without a structured way to attack these practical questions, even the most glaring anomalies will slip right past you when you're under that intense exam pressure. So let's break down the exact blueprint that top-tier students are using. And this framework right here is a total game changer. These 4 steps will transform an average, run-of-the-mill answer into a top-band Cambridge-style response. First up, identify the core physics concept. We're talking things like Hooke's law or the principle of moments. Second, you extract the exact evidence or data from the table or graph they give you in the question. Third, apply your scientific reasoning to tightly connect that data right back to the concept. And finally, package the whole shebang using the examiner wording we just went over. Seriously, if you run every single extended answer through these 4 steps, your exam paper is essentially bulletproof.
All right, let's put this framework to the test on a Total Classic. On Total Classic, the balancing ruler practical investigation. Take a look at this data. We've got forces and distances on the left side of the pivot and forces and distances on the right. In that first row, a 2 Newton force sitting at 30 centimeters perfectly balances a 3 Newton force at 20 centimeters. Then in the second row, 4 newtons at 15 centimeters balances 2 newtons at 30. You can clearly see the mathematical pattern emerging here. But the real question is, how do we articulate this using our 4-step framework to squeeze out maximum marks on a calculation question?
Well, let's put a heavily flawed student answer back on trial. And once again, I want you to play the examiner. A student looks at that balancing ruler data we just saw and writes this down. Can you spot the critical errors in their moments calculation? I mean, it seems like a simple enough conclusion at first glance, right? But I promise you, if this were submitted in the actual Cambridge 0625 exam, it would absolutely hemorrhage marks. Take a second, think about what is fundamentally missing from a strict physics-first perspective.
All right, let's bring out the red pen and compare that flawed answer against the perfect top band correction. So the flawed answer says, the ruler balances because the forces match. 2 times 30 equals 60. Wow. Okay, this is vague, it totally lacks correct terminology, and it has absolutely 0 units. Now, look at the perfect answer. Concept and examiner wording. Clockwise moment equals anti-clockwise moment. Scientific reasoning and evidence. 2.0 newtons multiplied by 0.30 meters equals 0.60 newton meters. See the difference? The perfect answer actually converts centimeters to meters to use the standard SI unit for moments, and it includes the absolutely critical directionality. That, my friends, is exactly how you win your case and get full marks.
Okay, time to escalate the stakes. We've mastered balancing a nice uniform ruler, but what happens if the shape is completely irregular? A massive core practical investigation in the syllabus involves finding the center of gravity of an irregular lamina, basically a random, weirdly shaped piece of cardboard. You can't just take a ruler and measure the middle. You actually have to use a plumb line, suspend the shape from a bunch of different pinholes, and trace the vertical lines to find exactly where they intersect. It's a classic multi-step practical question, and it's designed to test not just your conceptual knowledge, but your raw experimental design skills.
And whenever you're writing out the steps for that irregular lamina experiment, or really any practical design question, you absolutely must run through this mental checklist. Before you even think about turning the page of the exam, ensure you've included the correct units for every single measurement. Check your significant figures. They have to match the precision of the instruments you're using. If you have to plot a graph, optimize those scales so your data takes up way more than half the page. Always identify practical uncertainties, like, parallax error when reading a ruler. And always, always state a relevant safety consideration. These are the mandatory final checks the examiner is actively hunting for to award you those elusive method marks.
So the verdict is officially in. You survived the trial of calculations, you masterfully spotted the anomaly, and you fixed that flawed moment's answer. You are now armed with the exact framework to handle any calculation and practical setup they throw at you. But a hidden trap remains. You can have the most perfect calculations and flawless units, but what if the way you analyze your graph leads you to a completely false conclusion? What if you pull the wrong gradient or misinterpret the y-intercept in a way that just completely destroys your final evaluation? That right there is the exact trap that catches even the highest performing students totally off guard. To secure your final grade, you have to know how to navigate the hidden data analysis traps that the examiners explicitly warn about every single year. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click the explainer on screen right now to uncover the most critical examiner report mistakes. Because think about it, if your calculations are flawless, but your data analysis is a trap, did you really solve the physics at all? Click the explainer on screen now, and I'll see you in the next one.